Hey everybody, welcome back to Data Mining and Predictive Analytics. I am Dr. Nick Bolton, and today I'm going to talk to you guys about the supervised machine learning algorithm K-nearest neighbor. And what I've done here is I've put some notes together for you guys that are based on the PowerPoint presentation that you guys can find up on Blackboard. But what I've done is just gone through that PowerPoint presentation. This is chapter 12 from our Data Mining and Predictive Analytics textbook. And I've gone through and just highlighted some of the big things, filled in some gaps that I want you guys to understand, and really highlighted the big points that I want you guys to get away from this particular lecture. So if you remember back when we first started talking about machine learning algorithms, we talked about supervised and unsupervised machine learning algorithms. So supervised algorithms, you need to know something about the outcome of that data set. All right, so you could have a data set. Typically, this is a column that is labeled as outcomes, but it's some kind of classification variable where you have things like cancer or not cancer or something else, some type of classification variable. All right. And the way that we're going to train these models, and not just the K-nearest neighbor model, but most of the machine learning models that we'll create from here on out, all right, are going to use an industry standard for these supervised machine learning models, and that's based on the 70-30 split. All right, where 70% of our data set is going to be used to train the model, all right, and then 30% of the data set is going to be left off to the side. And now once we have a model trained and created, all right, in a certain kind of way, we then take in that 30% that is left off to the side, bring that in, and test our model to see how well it's performing. All right, and then we'll actually report the accuracy, how accurate it was at being able to predict that 30% testing set. All right, that testing subset. All right, so hopefully you guys will do this pretty much for all the models that we'll be looking at throughout the rest of the semester. All right. So the first thing we want to talk about is how does the actual K-nearest neighbor algorithm work? All right. Well, we can look at a particular example of looking at diabetes patients. All right. So say we have a doctor that wants to know what drug to prescribe a particular diabetic patient. All right. And we've had a data set that we've collected on different patients at different ages and looking at their blood sugar ratio, which is a measurement for understanding how diabetes is present, and it's really used to understand what drugs you want to prescribe a patient based on their blood sugar level. All right, so we have that data set, and we can create a simple graph here where we see that at a certain age drug A was prescribed, at a certain other age drug B was prescribed, and at an older age drug C was prescribed. All right, and so we train a model, a K-nearest neighbors model based on this these particular attributes, and then we have a new patient that comes in, all right, and we want to know what drug we want to prescribe them, all right, based on the prescriptions that we have prescribed in the past, all right. And so how do we determine that? How do we understand, or how do we prescribe this new patient? What drug do we prescribe them? All right. So we can use the K-nearest neighbors algorithm for that, where K is the number of neighbors, all right, that we should include in determining which drug to prescribe this new patient. All right. For instance, if I were to look at just a K equals 1, which means I'm only going to use a single neighbor, all right, a single person in this algorithm to try to determine how to prescribe this new drug, all right, then I would prescribe drug A in this instance because they are actually the closest to the patient that we were trying to determine what drug they're going to get. All right, so because A is the closest to our new patient, drug A would be prescribed to our new patient. All right, and that's if we were to use a K equals 1. All right, we're just looking at one particular neighbor and the neighbor closest to that. All right, if we're going to use K equals 2, all right, that means we now have to look at 2 different neighbors, all right, around that new patient. All right, Well, now what do we have? We have drug A and we have drug B, or drug A and drug C, all right? Or drug B and drug C, all right? We have to have a way of determining which K's or which neighbors are going to fit that K equals 2, right? But at any rate, if I go anything higher than a K equals 1, I have to vote, all right? Because all three of these drugs only have one particular instance of them, all right? I have to vote, all right? And I have to determine which K's or which neighbors I'm going to use in this determination of our new particular patient, all right? So some of the considerations for determining this are, one, how many neighbors do I want to involve into this discussion, all right? So how many K's do I want to have, all right? The other thing I need to consider is the distance between these points, all right? So how do I measure the distance between each of these points, all right? And then for anything that is higher than K equals 1, how am I going to combine that info, all right, that information from two or more points? In other words, should all my points be weighted equally? All right, should there, some points be weighted more than others? All right, there are a lot of considerations to this combination. So first of all, let's look at how many neighbors. All right, there are a lot of different ways for determining how I'm going to pick my K value. Well, if I pick a small K, all right, oftentimes this can be affected by different noise, different outliers. If I pick a very small K, where I'm only looking at one particular data point, for instance, all right, I may end up just overfitting my data. And when I overfit my data is just basically memorizing the data points. So we want to try to avoid overfitting as much as possible. All right, we don't want our model to just memorize what the data points are in the data set. All right, we want it to be more generalized, right? So in general, we want to create generalizable models, right? And this goes for anything even outside of the K nearest neighbor model. We want to create generalized models, all right? And what I mean by generalized models means that if I bring in a new data set, all right, that 30% data set or any other new data set that I want to test or I want to put into my model, all right, my model should be pretty resilient, all right, to whatever new data I'm giving in it. And it should be just as accurate as whatever I tested it with or whatever I trained it with, excuse me. All right, so we want to create generalized models and we want to avoid overfitting as much as possible. All right, large Ks, all right, large values of Ks, all right, are less affected by noise, but oftentimes if there are interesting values that are, kind of local minimum or very interesting, those can oftentimes get overlooked, all right? And so those are, for instance, data points that may be very close, all right? But if we're looking at very large amounts of K, we might overlook that local drug that we need to prescribe it, all right? And so there are alternative ways to be able to find K, all right? One is using cross-validation. Cross-validation can help us determine a more accurate value for K, all right? Because we look at a lot of different training data sets. And so oftentimes, or most of the time, whenever we're training a model, creating a model for the first time, we want to try to use cross-validation, all right? And this means that we're going to try various different values of K with different selected training sets, all right? And so oftentimes you'll hear the term K-fold cross-validation, all right? Or 10-fold cross-validation, all right? That means that I'm taking 10 different training sets. I'm still taking that 70% of my data, my overall data to train with, but I'm now taking 70% that is completely randomized, 70% that's completely randomized, 70% that's completely randomized. All right, and then I'm alternating which ones I train with to see which ones I'm going to get the best results from. And then whichever ones I get the best results from are the ones that I go with. All right, so the hope is that by doing this, by randomizing the observations that I take as my 70%, and doing this over and over and over again, that's going to minimize the classification or the estimation error that I get in my model. All right. A very just rough route way of being able to do this for just determining K values. All right. Is the square root of the number of observations. Just take the square root, however many observations you have, just take the square root of that. You know, oftentimes if you're pressed for time or just need a rough cut way of being able to determine what K value to start with, you have no idea where you should even begin. This can oftentimes help you determine that by just taking the square root of the number of observations. Remember, observations are rows within our data set. All right. Another way of determining K is through a scree plot. This is where you take different values of K, starting with, I don't know, K equals 1 in this particular instance, and then going and then iterating up by different values of K. So K equals 1, 2, 3, 4, all the way up to some value. All right. And then measuring what is the accuracy of your cross-validation measurements at K equals 1. What's the best results that you got here? What's the best results you got at K equals 2? And so forth. Now, if you were to plot this, as you see here, as a K, the number of Ks versus the accuracy, this is what we call a scree plot. And what you would see is that, you know, as your accuracy is, in this case, going down, sometimes they go up, there will oftentimes be a jump, all right, at a certain value, all right, and this is what we call an elbow, all right. And so you kind of look for these particular elbows in this particular plot. And what you do is you just go back one, all right? In this instance, I would use a K equals 3, all right, as my starting value and see how good of an estimate or how good a K equals 3 for this particular instance works, all right? So that's really some of the best ways for being able to determine K, all right? We will use cross-validation for most of the training sets for our models throughout the rest of the semester, not just our K models, all right, but also for building things like neural networks, decision trees, all of that. You can use cross-validation for all your machine learning models, and it's highly recommended to try to reduce the classification errors as well. So, all right. The next thing we want to talk about is how we actually end up measuring the distance between our data points. So how do we determine which or how far away these data points are? There's a few different ways to be able to do this. The most common one that we're going to look at is the Euclidean distance. And so this is the one that's most often used, especially when we talk about K nearest neighbor and K means classification. These models oftentimes default to using the Euclidean distance. The equation, there's not a whole lot of equations that I throw at you guys, but the equation for the Euclidean distance, all right, is simple. The summation of the data points at x minus the data points at y squared, take the square root of that, sum it up. All right, you'll get the Euclidean distance between data points at different observations, all right? The most important thing to take away from this is that the scaling when determining the Euclidean distance is important. So large values can oftentimes overwhelm the influence of other attributes. So think about the example I gave with baseball, right? If you have home runs versus batting average, all right, the home runs are going to be weighted a lot more because those values can go anywhere from 0 to, I don't know, 35, 40, right? Whereas the values for batting average only go from 0 to 1, with most batting averages being, you know, around 0.3 or 0.2, you know. And so the home runs, where you have a larger scaling, are going to influence your data set overall more than that batting average actually will. All right. And so we want to minimize the impact of those large values, all right, by normalizing our individual attributes. And we talked about this when we talked about pre-processing. All right, but a couple of ways to do that is doing the min-max normalization and or the z-score normalization. Those are just two common ways of normalizing your attributes and putting them on the same scale so that one doesn't influence the model more than the other. Okay. So while Euclidean distance will look at how far away each of our data points are, all right, from one another, a combination function is going to actually provide us a way to be able to combine similar records or similar observations and help us make a decision for a new record. All right. And so when we're trying to combine these, we want to determine which way or how do these influence us when we're trying to make a new decision. All right. And so one way of doing this is by looking at a simple unweighted voting mechanism. All right. And when we look at simple unweighted, it's whoever has, in the K nearest neighbors model, whoever has the most votes is going to win. So if I go back to looking at my example when I'm looking at two attributes of blood sugar versus the age, all right, if I have, two observations or two instances of when we gave drug B here, all right, and 3 instances of when we gave drug A here, all right, our new patient comes in and their blood sugar level and their age ends up being right here in the black, all right. So I'm going to use, in this particular example, K equals 5. So I've determined either randomly or through a scree plot or, by taking the square root, all right, I've determined that my K is equal to 5, all right, which means I'm going to look at 5 data points, all right, that are the closest based on Euclidean distance from my new patient. So 1, 2, 3, 4, 5. That doesn't mean that I don't have other observations outside of this. I mean, I could have X's over here, all right, observations of drugs over here, whatever. But I've determined that K equals 5 in this instance, so I'm only using the 5 attributes or the 5 data points that are the closest based on the Euclidean distance to my actual new patient, right? All right. So when I do that, I tally them up, all right? And I saw that in 3 instances I gave drug A, and in 2 instances I gave drug B based on all 5 of these observations. Now, because of that, all right, and I'm using the simple unweighted voting combination function, whoever has the most votes is going to win. So in this instance, the drug A that I gave 3 times is actually going to be the winner in this instance. So winner, winner, chicken dinner for drug A. All right. And so in determining which drug I would give my new patients, the new X would equal drug A. All right. And that's using the simple unweighted voting, where we're just looking at the most votes are going to win out of my K equals 5. All right. With the weighted voting, all right, I may determine that even though I have a new patient, all right, some of those drugs or some of those instances should be weighted more heavily than the others, all right? And so in weighted voting, neighbors that are closest to my new patient should be weighted more heavily than the ones that are more distant away, all right? So in this instance, again, my K is still equal to 5, which means I'm still going to look at the 5 closest instances of records that are closest to my new patient, all right? The scaling or the voting system is still the same. I still gave 3 people drug A and I still gave 2 people drug B, all right? But in this instance, I'm going to weight drug B heavier because its distance is actually closer than drug A actually was. All right, so the distance between my new record and drug B is closer than my distance between my new record and drug A. So in this particular case, all right, with the weighted voting, I'm going to choose drug B as the drug that I would give to my new patient. All right. So these are two ways that K nearest neighbors actually utilizes neighbors for weighting. Oftentimes, we'll have to look at the actual function within our statistical modeling programming language to determine which way which models actually use either simple unweighted or weighted voting as its default parameters. You can usually change all of these parameters that we just discussed. But this is the most important things that I want you guys to take away from the K nearest neighbors information. The slides will be up on Blackboard for you guys to look at. If you're really interested in diving more into this and the mathematical discussions, feel free to check out Chapter 12 of our Data Mining and Predictive Analytics textbook. But that's all I've got for you guys today. I hope you have a great day, and I will talk to you soon.